Good day, grade 10 science students. Today what we're learning about is mirror equations. We use mirror equations because they help us locate an image more precisely. We just learned how to draw ray diagrams. We learned that we can make different types of light rays leaving an object, and where after they hit the mirror and reflect, they will cross at a certain point, which will locate the image. This is great, but it's not the most precise way to do business. So instead we use the following equations to help us figure out where the image is located. We also can figure out things like magnification, like how much larger the image is compared to the object. Now these mirror equations can be used in several different ways, and we're going to talk about one example to use them. Now focal length is equal to the center of curvature, sometimes called R, sometimes called C, divided by 2. This can be represented by the following. If our mirror was made from a sphere, we can clearly see the center, or the radius, right, of the center of the sphere to the vertex, which would be the far side. Now the focal length is exactly halfway between these 2 points. It's located right here. Here I'm setting up a ray diagram using protractor. The protractor is 5 centimeters across from the center of a sphere. So if this is 5 centimeters, then the focal length will be exactly 2.5 centimeters from the vertex. Reminder again, this is known as the principal axis. So if this is C, this is F here. Here you can see I've drawn a ray diagram and I've put the object at C. I've then followed the rules, going parallel to the principal axis, going through the focal point, and going through the focal point, and then going parallel to the principal axis. You can see that the image forms exactly at C upside down. Now how would we describe that? Well, we can describe that image in a couple different ways. We can say that the distance of the object is actually equal to the distance of the image. And the distance of the object happens to be 5 centimeters. And the distance of the image happens to be 5 centimeters. The height of the object, I'd actually have to measure it out and compare it to the height of the image, which I'm going to do so now. So the distance of the object is 5 centimeters, the distance of the image is 5 centimeters. The height of the object is positive 2 centimeters, but the height of the image is negative 2 centimeters, which means it is upside down. To find the magnification of the image, what we have to do is use this following equation. Magnification is equal to the height of the image divided by the height of the object, or it's equal to the distance of the image, negative distance of the image divided by the distance of the object. For example, we can actually just simplify that by just picking which one we want. So we don't have to do both or the whole thing altogether. We can just take the height of the image and divide it by the height of the object. For example, in my case it's negative 2 centimeters divided by 2 centimeters, which is going to equal to negative 1. This means that the magnification is negative 1 times. I also can do that by finding the negative distance of the image divided by the distance of the object. The negative distance of the image, well, would be negative 5 centimeters, and the negative distance of the object would be 5 centimeters. When I divide them, I still get the exact same answer. So this is saying both of these work. This is how you use the magnification equation. It's important to note that if your image ends up in the virtual world, the image is over here, it will have a negative distance. So let's see if we can do an example using these equations to solve a problem. The example in front of us says this. A concave mirror has a 5 centimeter radius of curvature. I know it's 5 centimeters because if my mirror comes from a protractor, we measure the distance from the side to the middle, we see that it's exactly 5 centimeters. So we can write 5 centimeters in for our radius of curvature. That's the center. So therefore, we know that if it's a C of 5 centimeters, our center of our radius of curvature, we know our focal length is going to be 2.5 centimeters. I know that because of the following. The distance between C to V is going to be double the length between F and V. So we just take the radius of curvature and we divide it by 2 to get our answer. So 5 divided by 2 is 2.5. And that is my focal length. It's a good idea to always write your givens down in a question. So I know my 5 centimeters is my C, which is equal to 2.5 of my focal length. I know my height of my object is 2.5 centimeters, and I know that the object is placed 10 centimeters from the mirror. I've changed this from 40 to 10 in your worksheet to make it a little bit more manageable to draw the diagram. So this is when we need to discover, again, the salt of the image, which means that we need to know HI, and we need to know the distance of the image as well. So the height of the image and the distance of the image is what I want to find. To figure that out, what we need to do is we need to find the relationship between image and object. And this equation describes the relationship between the image and the object. It's 1 over s, f is equal to the distance of the image, 1 over the distance of the image plus 1 over the distance of the object. And you can take a look, and what do I have here so far? Well, I have the focal length, which is 2.5, and I have the distance of the image. We don't know, we do know the distance of our object, which is 10. And this is what we have here so far. And what we need to do is we need to do a little bit of algebra for us to be able to solve this problem. What I'm going to do first is I'm going to bring this over to the other side of the equation. Remember, whatever we do to one side, we need to do to the other. So I'm going to subtract 1 over 10 from both sides of the equation and keep it equal. If you don't want to show this step, you don't have to. It's an extra step that helps with understanding. So now we have 1 over 2.5 minus 1 over 10. And this is equal to 1 over di. To solve this problem, what we need to do is we need to have common denominator. Now I know that 2.5 times 4 is going to be equal to 10. So I multiply both sides, the top and the bottom of this fraction, and then I get 4 over 10 minus 1 over 10. Now I can do this math quite easily once I have common denominator. If you really wanted to use fractions at this point, not use fractions but use decimals, you definitely can. But the advantage of fractions is they're more accurate because of lack of rounding. So now we have 3 over 10 is equal to 1 over di. When you're at this point and you want to find what di is, remember you can easily just flip both sides. There's more than one way you can solve this, but di over 1 is equal to 10 over 3, and di is going to be 10 divided by 3, which gives us an answer of 3.33. And it's going to be in centimeters. This means that our our image is in the real world because it's positive. So we've located the image, and we know it's 3.33 centimeters from that calculation we just did. Because it's positive, we know it's in the real world, and that means it's a real image. So you can type, when we figure out salt, we know it's real because it's positive in terms of its distance of the image. We also know that it's located between C and F. We know it's between C and F because we know C is 5 from the question. We know C is 5 from the question, and we know that F, which is half of C, is 2.5. So it's 3.3. It's somewhere between the middle between C and F. What we still have to figure out is the height of the image. Now we can do this a couple different ways. We know the other equation. At this point, because we know distance of object and distance of image, we can actually figure out the magnification. Magnification is taken by the height of the image divided by the height of the object, or it's found by taking the negative distance of the image divided by the distance of the object. So we could plug this in here, these two numbers here, and find magnification if we wanted. I'm not going to do that. I'm going to just plug them in, and if you'll notice, looking at my knowns and unknowns, I know all three of these things, and I have one unknown. So all I have to do is plug in my numbers that I know. So the height of my object was given to me in the question. It was exactly 2.5 centimeters. So it's 2.5 centimeters. The distance of the image is negative 3.33 divided by 10. We're then going to do some simple algebra, and the height of the image will equal 3.33 divided by 10 times 2.5. So again, if you want to know the algebra here, if you're weak with algebra and need a little bit of help, That's what I just did there. I then multiply that out. 3.33 divided by 10 times 2.5. And the height of my image is going to be negative 0.832 centimeters. Now what does that negative mean? That means that it is going to be inverted. And if you take a look, the size of this, we're going to say, is smaller. We started with 2.5 and we finished with negative 8.32. So it is a smaller sized image. To verify our answer for part B, what we're going to do is we're going to draw a quick ray diagram to do that. Now remember, my focal length is 2.5, my center of curvature is 5, the height of the object is going to be 2.5 centimeters, and it's placed 10 centimeters away from the mirror. So we're going to set that up now. So here's our ray diagram, 2.5 centimeter high object. This is 5 centimeters to from C to V, the vertex. The focal length is 2.5 centimeters. So we have to remember the rules. If we want to draw a diagram, one rule that we should always remember is go through F and come out parallel. And that's what we're going to do. So we're going to come out exactly parallel. Second thing that we're going to do is we're going to go parallel and come out the focal length. So again, this is limited by my ability to draw parallel lines exactly, and again to draw accurately. I've now completed my ray diagram. We can take a look. I'm going to draw my object now. Again, this is where they cross, so that left the tip of the arrow. Therefore, this is the tip of the arrow here. I'll complete my line directly up, best as I can. Not perfect, but there we go. We measure the height of the object, and the height of the object is negative, and it's negative 0.8 if you look at that. I know it's difficult to see on the ruler, so it's upside down, so the height of the image is negative 0.8 centimeters. And if you recall, that matches up very well to my calculation that we did in our math. If we look at the distance of our object, the distance of our object is 3. So the distance of my image is 3, not the distance of my object. Distance of my image is 3. And if we look at our previous calculations, our calculations matched up with that quite well. Not perfectly, and this is why we need to be doing calculations. We originally had calculated it should be negative 3.3. Well, I have, negative 8.32, and I have negative 0.8. The distance of the object, or the image, was calculated to be 3.33, and I have a distance of 3. So this is why our math is always better than our diagrams. That's it for today. Thanks, guys.